I want to introduce to you Terry Goodman. Here he is. And Terry is the founder and managing director of Intech Solutions, an information management consultancy specialising in data quality. The company's been going for 25 years, which is always a measure of something. Terry? So I'm sure we're looking forward to welcoming you to the stage and hearing about your information quality.
Thank you. This is a mouse? Just a question? Is this a mouse?
Do you have a mouse for this? Oh, clicker. It's a clicker.
This is a clicker.
Does that work?
So what do I click?
Big green button.
Thank you. How do I go back? Oh yeah, thank you. Okay, there we go. So I've learned something in 25 years. Okay, so I'm actually not going to talk about data quality, although that is something we've been doing for 25 years. But of late, we've been found something really interesting and something that's really gone leaps and bounds over the last 5 years, which is graph data analytics and graph databases in general. So that is the topic of my conversation. So graph databases. So I'll go over what I'm going to cover. So firstly, I'll just define what a graph database is, and then go straight into use cases. And in there, specifically, I'm going to give a bit of information out on the Australian Tax Office's use of graph database, where we actively involved, and they've, of course, approved this presentation. I'll talk a bit more detail of what a graph database is, and of interest, over the last couple of months, we've been talking to people about graph databases, and everyone I speak to starts their sentence by saying, if my understanding of graph database is correct, then ... So it occurred to me, and generally when we meet with people, they're all people in similar positions to us, they're generally data people. So it's occurred to me that people don't really understand what a graph database is, but do have an understanding of the concept. So I'll go into a bit of detail, both functionally and technically, of what a graph database is and what graph algorithms are. Okay? And then hopefully we have some time for questions. So firstly, to define what a graph database is. So that picture up there kind of tells its own story. So a graph database is, to read that out, graph analytics is a set of analytical techniques that allow for the exploration of relationships between entities. So the key thing is that it focuses on the relationships of the entities rather than the entities themselves. Okay? So if we have a look at that, it's representing a scenario in terms of how a customer is related to an order, is related to a payment. So key thing to point out is it talks both of entity data, such as customers, and a lot of transactional data. And as a general rule, transactions often relate entities. So it's all about the relationship between the entities. Organisations use graph databases to find similar profiles or similar entities, to uncover hidden connections that are not obvious to them, to recommend next best action. And the recommendation of next best action is how it could be, for example, for Netflix. You watch a movie, you see what movies you go to and what you like. So all that creates relationships between you and movies, as of all the other users. So that allows a graph algorithm to work out what's the next best movie you might want to watch next. That's one example. But a next best action might be, for a worker, how to approach a particular customer based on what actions have been done to other customers and what the result has been. Okay. Find most influential user and customer, and detection of communities. So often amongst the customer base, there's all these relationships amongst the customers, and identifying, exposing those relationships and identifying communities within clients is a key function, and also what drives the communities and what's the centrality of the community is another key function of graph databases. Google, LinkedIn, all the social media companies could not do what they do without graph databases. So to a very large extent, the development of these graph databases have come leaps and bounds because of those companies and what they've done over the last 10 years. A little bit of a use case of ATO, and I'll present this exactly as is. This is information that's been approved for release. Automated Network Grouping Identification Engine. ANGI is the acronym at ATO. So ANGI is a project undertaken by the ATO's Tax Avoidance Task Force together with the Smarter Data Program, which are two separate streams of work within the ATO. Its goals are to support the capture, visualization, analysis of large and complex networks of relationships. So they try to understand, and they have, this is a second iteration of it, an enhancement of it if you like, to understand how the various companies and taxpayers are all related one to another. And of course, it goes without saying that companies own companies, and they own companies, and people are directors of multiple companies, and they work for multiple companies. And companies don't act independently, they act as groups. So the goal of this project is to provide ATO staff with a full understanding of the clients they interact with at the level they require for their role. Okay? To enable a tailor engagement approach for each client. And that's actually where this concept of what's your next action is when you're dealing with a particular client for a particular maybe tax scenario, is exactly what action to take with that client or for that client is dependent on learnings of other clients in a similar situation, what actions were taken with them and what the result was. So if we're able to get that data all fed into a network analytics database, then recommendations of next action can be very useful. Support high volumes of data. So of course the ATO collects very large volumes of data, both in terms of transactional data and data about entities. In 2019, ATO actually engaged the service of McKinsey & Company in regard to the design of ANGI. McKinsey & Company identified that a native graph database would enable greater processing and speed performance. So one of the key advantages of graph databases is because of the way it holds it, it just has a huge performance increase trying to do specific network analytics which just is not possible in relational databases. Enable more information to be captured and exposed, and increase the visibility of complex networks and relationships and patterns of interest that exist amongst the clients. ATO rose an RFT for the requirement. Intech Solutions tendered the TigerGraph software product, which is the product I'll be talking about. So Intech Solutions, we chose TigerGraph to bid to the ATO because of TigerGraph's performance advantage and its native graph database. It just appeared an obvious fit. ATO awarded the contract to Intech and acquired the TigerGraph software. Implementation is currently underway, and Intech and myself and others are actively engaged with ATO on that project. So getting back more to what a graph database actually is. So first looking at it from the front end, most people are familiar with this, what a graph database looks like from that picture, which is in effect a collection of nodes or those circles in that picture, and edges being the relationship between the nodes as a primary way of visualizing data in general. So that's typically what you see when you look at graph databases. Simple graph databases are rendered by software on front-end screens. The data can actually be stored anywhere. So to get small amounts of graph visualized data, one can certainly get that from relational databases. Larger databases, they typically use key value pair databases, which is a different type of technology. and native graph databases, each being different types of data technology. I'll talk about that a bit more. Key message from this slide is that graph data visualization does not equal a graph database. So I've seen a lot of front ends built that show a graph, and that's all good and encouraged actually. But it's at the end of the day, if you're dealing with large volumes of data, then you really want to head towards a native graph database to handle the volume. So what is a graph database and why should I use it? So a lot of this is going over things you no doubt already know, but I'll point this out in a bit more detail. So firstly, relational databases. Relational databases generally have a schema defined by tables, which makes it reasonably rigid. You can add tables, you can maybe add a column to a table, but generally when you have a data model in a relational database, it's pretty rigid. It does offer high performance transactions and it's really built for transactional workloads. Complex analytics generally requires multiple tables to be joined multiple times and large table scans, which is not optimal for a relational database and generally provides poor performance in analytics, which is why people tended to move to key value. Key value database is one key facet of that. And a key value database is simply a system that stores a key and a value for that. Key value databases, in effect, have no schema. It just has a key and a value, and a key and a value, a key and a value. Now, that actually makes it very scalable. It's very easy to segment that and to let it cover multiple clusters and additional machines and scale to large volumes. So it does offer high performance, simple transactions. However, when it comes time to analytics, the key values are not, there's no knowledge of the data model or the data structure. It just knows key values. So it still often requires large scans of data. So your performance is then dependent on how your data is, how many nodes you have in your cluster, and you tend to get very big computers and large expenses that go with that in order to get the performance. So generally it offers suboptimal performance for analytics, although for analytics it's certainly better than relational databases. Native graph databases, the schema is defined by the relationships. So when we actually define a graph database, we don't create tables and we don't create keys. What we do to create are nodes and edges. So we'll take a node, call it a customer, and then we'll say a customer, or maybe a person. And we'll say a person works for a company, and a company may own another company. And those are all entities and relationships between them, and that is how the schema is defined. It can provide high-performance transactions, as can the other types of databases. It's got pre-connected entities with storage optimized to traverse the graph edges. And that's a key thing. The whole storage concept and the indexing is designed for very fast querying, traversing the graph edges. So try to look at one, how am I connected to my next entity, how I'm connected to my next. And that whole optimization provides it an enormous performance boost on like-for-like equipment, hardware, I should say. So it provides high performance, deep analytics. Now I'm using this word deep analytics, or deep graph analytics, and high performance graph algorithms. So next question is, what is a graph algorithm, right? So we're all being fast at something that you don't know what it is. So graph algorithms, and this is getting into a fair bit of detail here. So some people love it and other people hate it. And I was told to make sure I put the ATO case study and news story first, so that before this. But let me get into the detail of the graph algorithms. So one graph algorithm is deep link analysis. Deep link analysis is effectively where we take entities and we say, how are they connected? We can take one or multiple entities. In this particular picture, they're in red, A, B, C, D, and how these entities are connected. So, for example, I might search for myself and someone else and say, okay, these people work for the same company, or they work for a company and that company happens to have shares in another company, and that has a director here, and that's how they connected. So we can work deep connections, but deep meaning distant connections. The next type of algorithm is a pattern, so identifying patterns of relationship. In this particular picture, it's showing a very simple pattern where one person is connected to another person that's connected to some sort of an entity or an action. So, for example, a person makes a phone call to a person and that person buys a product. Now, that's a simple relationship. You might define as someone having an influence on someone to buy a product. And then we can look at the graph data to identify that relationship or that pattern. Patterns, more complex patterns, can be discovered. So one can have all these AI algorithms to discover patterns of fraud or to learn patterns of fraud, and then to look at your data to identify risks of fraud. Yeah, so that's all about fraud detection, pattern recognition for various purposes. Commonality. So we might take two entities and say, how are they common? Now, often this is used for entity identification. So for the past 25 years, we've been in single customer views where we take data and integrate it. Now, when we do that, the normal process is you look at the data and you try to work out, okay, they have similar names, same phone number, etc. But at the end of the day, you make an establishment to say it's either the same person or not, and you action that in your relational database. The graph database takes a different approach. It stores each data separate, and you could store, for example, an entity as in this diagram as A, another entity as B, and rather than say whether it's the same person, you say this is what's common. They have the same phone number, they use the same mobile, they were seen from the same IP address. But there are other things they may have that are not the same. So a graph database gives you a very easy way of visualizing commonality between entities. And the last one that I'm going to in detail is the identifying of community. I've already spoken about this a little. Is through graph looking at relationships, we identify communities and potentially the centrality. So what's in the middle of the community, who's the most connected person in the community, and how might they influence the community in general. So who are the people of influence in the community. Graph databases are often commonly used for geospatial graph analysis, temporal or time series, and various machine learning algorithms that happen on it. Some more examples. I'm going nice and quickly, I notice, so good news is we'll have some time for questions. So a deep link analysis. In this particular scenario or example, we're doing a search to identify how that person there, I can't even see their name, Lou, is connected to Jermaine. And excuse the names, I'd rather use different names, but so a click of a button would expose how they connected. Now, if we notice this is kind of connecting that person to a company who owns a company, who has own shares in another company, etc., etc., etc. So it's a very deep, there's 10 connections here as you go down. So 10 connections is a distant relationship, but there are 3 paths of 10 connections. Now, to try to search a relational database to identify someone 10 connections across would effectively mean you'd have to join the same table 10 times, which generally, from a SQL programmer standpoint, is just not done. And if it were to be done, it just would kill performance. And even most kind of suboptimal graph databases can't do this either. You really need a high-performance database to do this with any large volume of data. This is a very nice example of pattern discovery. This is a real use case. It's not done in Australia, but another country is doing this to identify a good phone from a bad phone. And I'll just describe what I mean by good phone and bad phone. So I don't know about you, but I quite frequently get phone calls or spam phone calls, messages from recorded messages that ATO, I owe ATO money and I must call them straight away, or they're coming to arrest me. So if you don't get that, I'm concerned because maybe it's true, but it's not. It's a spam phone. So what a particular country is doing to identify spam phone calls is loading all the data of every phone call and this is a telco doing this, so every phone call made gets loaded into a graph database to identify who's calling who. And then what happens is they've detected and worked out patterns of a normal phone behavior, which is for a person to call a person. So if I look there, someone makes a phone call to people. So I might call 5 or 10 people regularly, and I call them frequently, not just once. And then those 5 or 10 people substantially call each other quite often. So I call my brother, I call my mother, they call each other, I call Phil, and these people tend to call each other. That's a normal behavior of using a phone. On the other hand, in a bad phone that's used for spam, a phone number would just call someone and call someone else and call someone else, and the people they're calling wouldn't call each other on the whole. So a very different pattern of usage. So that allows one to automatically, in a system, in real time, detect a phone that is being used for spam. And then what this country is doing is, as you receive a phone call from a number that's tagged as a bad phone, the telco texts you straight away, and you can see this phone call is likely a spam. So I can then in real time choose to answer or not, knowing that the person ringing me is tagged by the telco as a bad phone. So quite a useful use case. And the key technology behind this is graph analytics and identification of patterns through a graph algorithm. Communities and centrality. So this particular example is showing clusters of people that work for companies that work on projects together. And it's able to identify these communities. Now, we could, of course, load this with more data of who's communicating with who and how and when to identify centrality and who the people in each of these communities are the most influential. And this could be used for all sorts of purposes in terms of trying to influence a group, understand how the group behaves, trying to sell to the group, try to generally understand how the behavior of a group and who influences them. The last example here is showing 2 people and what I spoke to before about commonality. So what's common amongst these 2 people? So it's still seeing kind of a spreadsheet and saying these kind of people agree with the score. Actually, what we're seeing here is the green nodes top and bottom are like the record IDs of the people. And you can see they share an address, they share a mobile phone number, they share an IP address and a device number, meaning they use the same phone. But each record is using a different email, and each record has a slightly different spelt surname. So one could match these 2 records, but one will have lots of records like this that they're not comfortable matching and saying they're the same person, but nonetheless they can use the fact that they have the same mobile data as a connection, use the fact that they're on the same address as a connection. So when you're traversing your graph and trying to understand how are these people connected, it can traverse through these data points. Okay. Questions? That was much faster than I thought.
Any questions? Yeah, a couple over there. Where's the mic? Here we are, we're running. Over at this table over here. Anyone else just signalling? Okay.
Thank you for the amazing talk. Just first of all, the comment, thank you for sharing the graph databases in the conference, because I think this is amazing. The graph database has an amazing potential when you have a huge amount of data, and particularly when you have a network architecture at the back end. So in terms of the analytics side of things, so what are your understanding about how much data that you would need to generate meaningful insights out of the analytics? So do you need a graph database to set up, or can you work with other databases to do graph analytics? And second, what is about, I just wanted to share a thought that as you shared a lot of demonstrations there, one of the demonstrations that we currently using at the transport is how do we represent our transport network in a graph structure so that we can quickly generate insights. If you knock down a particular node, what's going to happen downstream? What are the signals that's going to affect, and how to quickly recover the network from being, let's say, congested? And some more potential applications I'm happy to share with others if they're interested.
Okay. Yeah. So there's two questions there. So how much data do you need for it to be meaningful? Actually, I kind of heard two questions. How much data do you need for it to be meaningful? Can graph algorithms be done on other databases? Which I'll probably answer first because it's the easiest. So yes, graph analytics can be done on any type of database. However, if you're trying to do something in real time with large volumes of data, then it really the database ought to be optimized for the use. So, which is a graph database. So large volumes, you'd want graph database rather than other databases. Small volumes, yes, you can do from other databases. In terms of the amount of data that's needed to be useful, it's a good question. I don't really have a good answer for that in truth. However, generally people load these graph databases with very large volumes of data because they tend to store transactions very well. So in terms of a transport network, you would want to store locations, streets, suburbs. But the key thing that your key volume of data would be trips of where people are going. So a trip of where someone might be catching. You would load it with bus stops, and then people getting on and off would constitute a trip, a movement of a person. You might be scanning number plates of cars traveling across roads. Every time they pass, they've seen here, that's a trip. So you'd get, a million. If I think about Sydney, not in weather like today or yesterday, but normal days, millions of trips a day. So the volume of data coming in is very large. What is common with these graph databases is that it's not necessarily used to be your everything. So when you want to look up information about a person and see everything about them, you would normally look up a relational database. However, when you've got a person here and all the trips they do, you would store the minimum footprint of that in your graph database to identify your graphs, your actions, your trips. Or earlier today, there was a utilities with water supply. So, that made me think also can be modeled in terms of graph data. So what I have seen, and for 25 years I've been doing data modeling on relational databases, so it was a shift, is a shift I should say, but it's the same exercise. So you can model things in a graph database way with slightly different thinking, but graph data modeling is really the same discipline as relational data modeling. So if you're a data modeler in a relational database, you need to unlearn that in a way, but the skills are the same, and any scenario, including transport, can be well mapped and modeled. Yeah.
Okay.
Just quickly on that, because that's exactly where I was going. So I've been doing relational data modeling for a long time, and so it's like, is it a new discipline, or is there a new technique that you're doing? You're leveraging your existing third normal form, but going somewhere else with it.
Yeah, it is a different mindset. So I would say you use the same skills, but in a different way. So if you've been doing data modeling for a long time, then you need a bit of practice, and you find a scenario and you model it in a graph way, load it with data, see the pros and cons of what you did, and then you can load the graph a little differently, see the pros and cons of what you did. You can't do that 3 times, and then I wouldn't say you're an expert, but I would say you would have learned a lot and be pretty capable of modeling graph schemas. Yeah, that was my experience anyway. Don't know how much more time there is, but
well, we'll take one last question.
Thank you. Yeah, it's really fascinating. presentation. Here, I got a question, say, in terms of the graph, in your example, we say the visualization or the final pattern, I think it's fairly straightforward or probably not that complex to showcase some example, right? So we can see the local what network look like, but we quite often when we think of the patterns or commonality, it's quite difficult to come up with a narrative or come up with aggregated view in terms of visualization, in terms of present those patterns. Say if we want to convince SES to say we want to use graph algorithm or build graph database, we want to say this is the real impact to the agency or to the department. That view, I think we found quite difficult. So I just want to ask your experience or your expertise. How do you guys manage that bit of the graph?
Yeah, okay. So in terms of loading data and coming up with demos that show real things, yes, it actually is quite easy. So it is quite easy to kind of, when you forget about all the really hard parts and you think about the core thing that you need in trying to show, is you can typically create a couple of entities, a couple of relationships, and then query that and show quite a bit of meaningness from that quite quickly. So it is actually something that, in my view, is actually faster to model and trial and see some result than a relational type scenario. And the visualization's already all very pre-built in a way, because you've got a tool that does a general visualization on a graph. In a relational database, you kind of don't. You have to build your whole application as well. So it is actually easier to model. What I can say is ATO's way that they got their business case through is they got McKinsey to go and do a whole big story, and they reached the outcome, made a recommendation, and boom, it happened 2 years later. So, you know, that was someone else's approach. So yeah, but certainly to model it, I'd encourage you to do that. Yeah, it's quite effective.
Okay, thanks, Terry,
Okay.
for coming to the